Before we get started talking about hypothesis testing, I want to suggest this is one of my favorite websites. I've probably talked about it before or posted about it. It's called Khan Academy. Khan Academy is one of the best online resources for statistics or plenty of other topics, really. Just go to khanacademy.org and you can find their math section. Click on Learn, and statistics is located in the math section. I have a friend that is in math that would argue with that category placement, but regardless, there are a bunch of lectures on most of the topics that we're going to be covering in this class have a lecture associated with them. And there's a lot of other stuff and unique perspectives that you won't be getting in these lectures, but that are equally valid and make a lot of the topics easier to understand, getting a second perspective. Okay, so we have talked a lot in this class about samples and populations, and you should know by this point that there is a link between samples and populations. Most often we want to have information about a population, but we can't test the whole population. So instead we have information from a sample. So how do we get from the sample to the population? One way to do this is called a hypothesis test. So a hypothesis test is a statistical method that uses sample data to evaluate a hypothesis about a population. That is from your book. So just to review what a hypothesis is, the general definition, a hypothesis is an educated guess. Hypotheses in science must be specific and testable. In this class, how are we going to test hypotheses? With numbers. And what kind of numbers? You guessed it, with statistics. We are going to calculate sample statistics for use in inferential statistics tests to test hypotheses. So this lecture is going to be all about how that process takes place. Hypothesis testing has 5 steps. Now there's an additional lecture that should be up on Blackboard already that goes over each of these 5 steps in detail. After you've watched this lecture, after you've read the book about t-tests especially, I would go watch a quick lecture and see if you understand everything that's going on as kind of a content check to see if you're getting hypothesis testing. Right now, I'm just going to list the 5 steps, go through them pretty quickly, and then explain where they come from, why they're necessary. Step 1 is always state hypothesis. There's a specific form for hypotheses for every inferential test that we'll be going over. Step 2 is set the criteria for what you would consider a proof of the hypothesis. So proof is a bad word, I shouldn't use it. But what you would consider good evidence that your hypothesis was shown to be true or not. Step 3 is to obtain the sample that you're interested in and compute a test statistic based on that sample. The first few examples will be computing the t-statistic through several different techniques. Then later on we'll use other statistics. Step 4, compare the calculated sample statistic to what your null hypothesis would have expected you to find So we're going to come up with a null hypothesis and an alternative hypothesis that I'll talk more about later and make more sense in context. And step 5 is making a conclusion about your hypothesis. Was your hypothesis supported or not? So let's go through an example of this. And this process, by the way, takes place for the rest of the class. Now, while these 5 steps are going to be different from test to test, this 5-step framework is what I would like to see on homeworks and tests and quizzes. Because number 1, this is a very good way to organize hypothesis testing. Number 2, it makes sure that no steps are missed. Each of these 5 steps is important for different reasons for the process of hypothesis testing. So I'd like for all answers to be organized in terms of these 5 steps. So why do we need this hypothesis testing approach? I'll go through an example of when we might want to use this. So let's say that someone named Blaise Pascal decides to sell calculators. And he has the idea that pink calculators are going to sell faster than any other bland colored calculator. So his idea is that pink calculators will sell better. So his hypothesis is that pink calculators will sell better than calculators in general. So the next step is to state criteria. And this is what evidence will we take to show that pink calculators sold more than calculators in general. And he says, well, if they sell more in a week than calculators in general, then that will be support of my hypothesis. So we obtain a sample. One shop sells only pink calculators for 1 week. And then we compare the sample to the null hypothesis. In this example, we would compare the pink calculators sold to calculators sold in general, and then make a conclusion about the null hypothesis. So let's say that in 1 week, an average of 40 calculators are sold in general at other stores, but the store selling only pink calculators sells 60 in 1 week. What conclusion would you make based on that information? Now, this is a statistics class, and we've talked about things such as the mean and the standard deviation up to this point. Let's go through this in a little more detail. When we state the hypothesis, one thing that we need to be aware of is, so the example I've given on the slide before is kind of a rough cut without the necessary refinement for what we're going to be doing in a statistics course. It has the same general outline, the 5 steps, but we need to be more specific. First of all, when we state our hypotheses, there's a specific form that our null hypothesis testing needs to take that we're going to be going over. Second of all, when we state a criterion, we need to make reference to the alpha level, a concept we'll look at more in this lecture. Third is that when we obtain and compute a sample statistic, we'll be computing specific to statistics, such as t-statistics, that will be discussed in this lecture. Fourth is that when we compare the sample to the null hypothesis, we'll need to be using a specific approach that we'll be going over before we make our conclusion. In hypothesis testing, if the individuals in a sample are noticeably different from the individuals in the original population, we have evidence that the treatment has an effect. But it is also possible that the difference between the sample and the population is just sampling error. So going back to this example, we see that in 1 week, 60 pink calculators were sold at a store, when normally only 40 calculators are sold. But, well, forget that one. This is the important one. Although an average of 40 are sold per week at other stores, the standard deviation is 15. So considering we have a mean of 40 sold with a standard deviation of 15, would we consider 60 sold for pink calculators an unusual score? So we have the tools now to decide whether the number 60 is unusual. Is 60 very different from 40, considering we have a standard deviation of 15? In this case, we can go back to using z-scores. The total calculator sold is an example of what we consider the population, and the sample were the pink calculator sold 1 week at one store. So using z-scores, what is the z-score for the store that sold 60 if the population mean was 40? So if you've calculated the z-score for the raw score of 60 would be about 1.33. So that's 1.33 standard deviations above the mean. Now, remembering from our chapters about z-scores, we know that 1.33 standard deviations above the mean that's pretty far above the mean. There are many scores below that. That's kind of atypical. But we'll be going over in the null hypothesis testing approach, but so that we don't have to decide every time, well, should we consider that score typical? Should we consider it extreme? Is the difference large enough to justify making the conclusion that they are really different? We don't want to have to come up with those criteria every single time we perform a hypothesis test, or we try to compare two results. This is where having a standard way to compare the null to the alternative hypothesis, to compare the obtained statistic to what we would expect, is important. Okay, so let's go back to square one. A statistical hypothesis is an assumption about a population parameter. So, like I said before, the best way to determine whether our hypothesis is true would be to examine an entire population. This is impractical and most of the time impossible, so instead we use a random sample as a stand-in for a population. We use this sample, this randomly collected sample, to test our hypothesis on. Now, whenever we test a hypothesis, there are two possible explanations. One is we could determine that the difference between the sample and the population can be explained simply by sampling error. And our second conclusion is that the difference between the sample data that we collect and the population parameter is too large to be due to sampling error. In the first case, when we say that there is no difference, we can also say there is no treatment effect. In the second case, in which the difference is large enough, we might say that there is a treatment effect. A note on terminology: I'm trying to be careful not to use the word prove. We cannot prove things to be true in statistics. We can show evidence for one conclusion or another, but there's no proof. This is why the null hypothesis testing approach is kind of counterintuitive, because the null hypothesis testing approach is actually, once we get into it, set up to fail intentionally. The null hypothesis testing approach that we're going to be going through is set up in such a way that we are more likely to show that there is no effect. We'll go over the reasoning for this as the lecture progresses. So, when we have a research hypothesis, these questions must always be translated into the language of parameters in probability models. What this means is that the only answerable questions we can tackle in statistics are those that can be addressed by comparing the numbers we obtained in a sample to the real or the theoretical numbers from a population. So, when we ask the question, is there a real effect, or is there a real change in numbers, we are asking this question in the framework of having a null hypothesis. We always posit a null hypothesis that says there is no effect, and an alternative hypothesis that says there is an effect. So rather than having one hypothesis that we're going to make conjecture about, there's always going to be two hypotheses, the null and alternative. This is an integral part of the null hypothesis testing approach. The reason being is often when we are performing an experiment where we are trying to find an effect of something in the world, this technique is biasing our experiment against finding an effect. And that sounds counterintuitive. So why should that be? Let's say that we are a pharmaceutical company and we are trying to find if our new heart medication reduces heart attack rates in a population of elderly people. We have a lot of vested interest in the drug actually working. By setting up our research hypothesis with the null hypothesis testing approach and biasing it against finding an effect, this is one way of us counteracting the natural tendency to bias our own results for finding effects. It's a safeguard against finding an effect when there is not one. One thing that you might want to look up, it's been in the news lately, is the replicability project in psychology. The replicability project, I think, started in 2013. It's very recent. Started in 2013. Is an effort by psychologists to go back and try to reproduce effects, classic effects that have been found in psychology, to make sure that these effects can still be replicated today after the original researchers have published about the phenomenon. In a lot of cases, the replicability project or reproducibility project has found that classic effects in psychology hold up to modern scrutiny and modern statistical techniques. There are some examples, however, of classic effects in psychology that were not found again. So how is it that someone can find an effect, a psychological effect, publish about it in a psychological journal, and get away with that? How does that happen? We'll be talking about that in terms of type 1 and type 2 error rate here shortly. Okay, so this is all part of step 1 in the 5 steps of hypothesis testing. We want to set up the null hypothesis. The null hypothesis is written as H0 or H0 works. H0 says there is no difference between the sample statistics and the population parameters, or in some statistics tests, such as independent samples t-test, it says there's no difference between samples. It all boils down to there being no difference between the population we are studying and the population of all individuals. The null hypothesis includes the room for error. This is any minor differences are due to chance. The alternative hypothesis, which can be written as a symbol as H sub 1 or H sub A, says that the difference between populations is not due to chance alone. It's due to some non-random cause. It could be a treatment effect, it could be something else. So the big difference between the null hypothesis and the alternative hypothesis is that the null hypothesis says that there is no difference, or if there are small differences, they are caused by chance. The alternative hypothesis is the assertion that there is a real difference and that it is not due to chance. It is not due to sampling error. A quick note, so our hypotheses are always stated based on populations. So you'll notice that's going to be the consistency through the examples, that our hypotheses are always stated, like right here, in reference to population. So this is the example of a null hypothesis for a t-test or several others, as mu0 is equal to mu1. So, like I said before, the null hypothesis states there is no difference between populations. Our alternative hypothesis says mu0 is not equal to mu1. So our alternative hypothesis says that there is some difference between these two groups. We'll be talking more question about whether a statistical test is a one-tailed or a two-tailed test. Let's save that for in a minute. So this just says the population means are not equal. Now, let's bring this back to what we were talking about, the distribution of sample means in previous lectures. Now, bringing it all together, if we have a set of raw scores and we create a distribution of sample means from a set of data, this distribution of sample means, if it fits the proper criteria, is going to be normally distributed. So, remember, if we have a set of data and we randomly pick one sample from this distribution of sample means, chances are more than likely that the random sample that we pick is going to fall somewhere in the body of that distribution. Sample means close to the null hypothesis are going to fall close to the center of this distribution. Sample means that are less likely to be chosen fall to the tails of this distribution. And this is really what the null hypothesis, or the alternative hypothesis represents, is extreme low probability values. If we find an extreme low probability value as our sample mean, this indicates that the null hypothesis is less likely to be true. Now, let's talk about the direction of tests. So, when a research study predicts a specific direction for the treatment effect, so an increase or a decrease, what it means for a hypothesis test to be directional is that rather than hypothesizing that a treatment effect will cause a change in a population, the hypothesis states that a treatment effect will cause a specific directional change. So either will increase or decrease an effect in a population. So looking at that mathematically, or in mathematical notation, if the original population mean is 80, and a treatment is predicted to increase the scores of this population, then the null hypothesis would state that after the treatment, the mean after the treatment is less than or equal to 80, basically saying there is no increase. And in this case, the entire critical region would be located in the right-hand tail of the distribution. What does this mean? For our alternative hypotheses, they'll always state for a directional test or a one-tailed test that one mean is greater than the other, or one mean is less than the other. Okay, let's go through the 5 steps of hypothesis testing in detail. Step 1, we want to state our hypotheses and select an alpha level. Our null hypothesis always states that the treatment has no effect. So remember, we always start with a null hypothesis. Now, what is the alpha level? The alpha level establishes a cutoff point for making a decision about the null hypothesis. Remember, I was talking earlier about, so if we do find a difference between two populations, how do we decide whether that difference is big enough to say this is probably not due to sampling error, this is probably due to a real difference? The alpha level determines the cutoff point and is an accepted standard cutoff point for deciding whether something is truly different or perhaps due to sampling error. So let's have, I'm going to have a little discussion about why we often use the cutoff point of alpha equals 0.05. So in the past few chapters, and you see on your homework assignments, we use the cutoff points of typical or extreme to describe scores. So we said that scores that are within 2 standard deviations or within 2 z-score of the mean were considered typical, and those that were outside of 2 standard deviations were considered extreme. We're going to mostly abandon this approach in the coming chapters because we want to use a more stringent cutoff point, a more strict cutoff point. The alpha level of 0.05 is a traditional cutoff point in psychology. The reason that 0.05 is used, number one, is that it's a good round number. 05 is an easy number to remember. 95% chance of certainty is just a good cutoff point. But it also is a good balancing point between the types of error that we'll be talking about in the coming discussion. So 0.05 is a good number for you to remember for the coming discussion. Now, you can see here that for alpha level equals 0.05, that the z-score cutoff point is 1.96. So it's pretty close to the cutoff point of 2 that we've been using in previous lectures. We could use a smaller alpha level of 0.01. This makes it much harder to determine that there was a significant difference between the two groups. By increasing the z-score that we would need. The more that we lower the alpha level from 0.05 to 0.01 to 0.001, the smaller the critical regions at the tails of the distribution become. And the smaller the critical regions at the tails of a distribution become, the more difficult it is to show that we have a treatment effect. And more difficult to show that we have a treatment effect doesn't mean necessarily that that's a bad thing. So step one is we've set our alpha level. For most questions that we're going to go over, our alpha level is going to be assumed to be 0.05. So step two is to locate the critical region. So the critical region of a distribution consists of the outcomes that are very unlikely to occur if the null hypothesis is true. So the critical region is defined by sample means that are almost impossible to obtain if the treatment has no effect. And the phrase almost impossible means that these samples have a probability that is less than the alpha level. So I really like to look at distributions visually to see what we're trying to get at here. So if our mean from the null hypothesis is 80, as in this example, if we find that our sample mean is close to that population mean of 80, then that is the region in which we would say that our null hypothesis is true. If we find a sample mean that is outside of the center of the distribution, and it's so far outside of the center of the distribution that it has a z-score that is less than 1.96 or greater than, or less than negative 1.96 or greater than positive 1.96, we say that that sample mean is in the critical region. Now, if you, so for an alpha level of 0.05, what we're looking at here, shaded in blue, is the part of the distribution that makes up 5% of the distribution at the tails. You can double check this yourself in the Z table in the back of the book. Above 1.96 is about 2.5% of the distribution in total. below negative 1.96 is about 2.5% of the distribution in total. So, step 3, after we've identified the critical region, is to collect and analyze data. Step 3 is where we are going to compute a test statistic. The test statistic forms a ratio comparing the difference between means versus the amount of difference we would expect due to chance. Now, right here, this definition is going to become very important for the rest of the class because this is the general form of all of the test statistics that we will be seeing the rest of the class, is a ratio comparing the actual difference divided by the amount of difference you would expect due to chance. So the test statistic in this chapter will be z-scores. Forms a ratio comparing the obtained difference between the sample mean and the hypothesized population mean versus the amount of difference we would expect without any treatment effect, which is the standard error. And after we have calculated the test statistic, we go to make a decision. A large value for the test statistic means that the mean difference is more than would be expected by chance. If the difference is large enough that it is in the critical region, we say that the difference between the treatment mean and the population mean is significant, and we reject the null hypothesis. If the mean difference is relatively small, which means that it's not in the critical, anything that's not in the critical region, then we fail to reject the null hypothesis. So in the null hypothesis testing approach, we'll either reject the null hypothesis or fail to reject the null hypothesis. Our conclusions are always framed with regards to the null hypothesis. So, this rejection approach that we've been talking about, we select a criterion, we perform a test, and if the probability of obtaining that result is less than 0.05, we reject the null hypothesis. So this is the technique that we're talking about in this lecture. That's why it sounds so familiar. I just want to make it clear that this technique that we're going through is only one approach to statistics. And currently it's not the most popular approach for many statisticians and many psychologists. There are problems with this null hypothesis testing approach that we won't necessarily get into. It won't be tested on them. But just know that there are alternative approaches, some of which we'll talk about in this class, to the null hypothesis testing approach. One problem that we'll talk about right now is that both of these probabilities listed on the screen would result in us rejecting a null hypothesis. If the probability of obtaining our result is 0.048, that is below that cutoff point of 0.05. That would lead to the same conclusion in the null hypothesis testing approach as a much smaller probability, 0.00001. We won't necessarily get into that in this lecture. So step 5 is make a conclusion or describe what happened. So put into words what our hypothesis test result means. Okay, so when we're dealing with sample data, there's always the issue of sampling error. Now, we're going to introduce two new terms, type 1 and type 2 error. And it's important to remember that these are two separate categories. Sampling error helps lead to the chance of making a type 1 and a type 2 error. But sampling error is something that is always present when we are taking information about a sample and trying to apply it to a population. Type 1 error and type 2 error are mistakes that researchers make. So, sampling error is inevitable. It happens in every case where we are sampling something. Type 1 and type 2 error are mistakes that can happen that an experimenter or researcher does. So, a type 1 error occurs when the sample data appear to show a treatment effect when in fact there is none. So what does this mean? Type 1 errors are caused by unusual, unrepresentative samples. Just by chance, the researcher selects an extreme sample with the result that the sample falls in the critical region even though the treatment has no effect. Now, the hypothesis test is structured to minimize the type 1 error rate. The hypothesis test is structured to minimize the type 1 error rate. When we set the alpha level, we are setting the probability of a type 1 error rate. So the alpha level, if we set the alpha level lower, we are lowering the probability of a type 1 error rate. Type 2 errors is when the sample does not appear to have been affected by the treatment, but the treatment does have a real effect. So in this case, the researcher would fail to reject the null hypothesis and falsely conclude that the treatment does not have an effect. Type 2 errors are commonly the result of a very small treatment effect. So a type 2 error will often happen when there really is a treatment effect, but the real treatment effect is too small for the statistical test to pick it up. So this 2x2 matrix that you can find in your book is my best. This is always the easiest way for me to understand type 1 and type 2 error rate. So on the left, you'll see this is the experimenter's decision, and at the top you'll see there's two possible actual situations. Now, we hope that it is the case that if an experimenter rejects the null hypothesis and the effect actually exists, then in that upper right hand corner we make a correct decision. We hope that if an experimenter conducts a test and says we should retain the null hypothesis and there's actually no effect, then we've made a correct decision. That's the bottom left hand box. But there's always the possibility that we will reject the null hypothesis when there is actually no effect. That's a type 1 error. Or we can retain the null hypothesis when an effect actually exists. That's a type 2 error. Type 1 errors are, in most cases, more costly to the scientific process, more costly to experimenters. If a researcher asserts that there is actually an effect and there is not one, it was due to sampling error that an effect was found, this can lead to wild goose chases in the scientific process that are costly in terms of resources. It can also lead to false assertions. For example, if a drug company finds that their, let's say they have a medication to cure a medication to ease insomnia, and they perform a statistical test and find that their medication does have an appreciable effect on lowering insomnia rates. If this is a type 1 error, then they have put that drug on the market when it actually doesn't work. It doesn't have an appreciable effect. Okay. So let's go through an example from start to finish of the null hypothesis testing approach. So through the 5 steps of hypothesis testing. So this example is what effect does alcohol exposure have on birth? So if rats are exposed to alcohol during birth, does it change their litter's weight? So a pregnant rat is exposed to alcohol during the pregnancy. Does that change the litter's weight? That is our research question. So step 1 is to take our research question and form it into hypotheses that fit with statistical interpretation. So we need to put numbers in there for our research question. So for our null hypothesis, let's say that rats normally weigh 18 grams at birth. So we need to write out our null hypothesis saying that the mean for the alcohol exposure condition rats will be equal to the mean for normal rats. Either form of the null hypothesis on this slide would be correct. Either put it into words, the mean for the alcohol exposure is equal to the mean for the normal group, or if we have the number, we can include the number there. We're not going to use a directional test, but you can see the null hypothesis for a directional test at the bottom of this slide. Okay, second part of step 1 is to formulate the alternative hypothesis. In this case, we just need to say that the mean for the alcohol exposure condition is not equal to the mean for the normal condition. We can select our alpha level in step 1. We want to select our alpha level of 0.05. That means that we have a 5% chance of committing a type 1 error. So alpha level 0.05 means we have a 5% chance of committing a type 1 error. So step 2, select criterion. We want to identify the critical region, the region in which if we find an outcome there, it means it is very unlikely the null hypothesis is true. If we are using a two-tailed non-directional test and we're using z-scores like in this example, then the cutoff point, the critical regions are going to be defined by plus or minus 1.96 in terms of z-scores. We can look at this visually. We can first of all look this up in the book because memorizing these numbers is useless. There's too many numbers to memorize. This is probably the only one that you kind of need to know the ballpark of where this one is supposed to be. I like to look at it visually. We can look this up in the back of the book under the table for the probability for z-scores. We are not using a one-tailed test, which is the top 2 pictures in this slide. We're using a two-tailed test, and we can look up and see that the bottom 2.5% and the top 2.5% of the distribution, the cutoff point for these is plus or minus 1.96. So in this example, we can write that out as Z sub CV, stands for critical value, is equal to positive or negative 1.96. Now, notice here that the Z values on the bottom of this slide are for the one-tailed test. Okay. Here is some alternatives. If we were not using alpha equals 0.05, if we wanted to choose a more stringent alpha level, then we would have to use the more stringent Z values found here. I want to make note here of the difference between the alpha level and the critical value. They both kind of give the same information, but they're talking about two different things. The alpha level is a probability. The critical value is the z-score at which we would find that probability. So both of them are similar concepts, but they're finding two different things that will always be related. So let's go on to step 3, which is collect data and compute a test statistic. So in this case, we can use a one sample z-test, which is outlined in the chapter. Let's say that we have capital M, a sample mean, and we want to compare that to mu, the population mean, and we have the standard error, which is at the denominator, sigma sub m. So this is the one sample z-test. So let's say in this example that we have a sample of 16 pups. The mean weight is 15. We already said that the mean weight for normal pups is 18. And in our sample, we see that the mean is a little bit lower. So let's test and see if the statistical test puts us in the critical region. So we have the standard deviation of the population, which is 4. So we use that to calculate the standard error of the mean. And then plugging these values into the z-test, the one sample z-test, we get a z-value of -3. This is our test statistic for this case. Okay, so if we have a z-value of -3, our critical region was plus or minus 1.96. What does this mean? Is the sample mean in the critical region or not in the critical region? Well, we can compare and see that a z-score of -3 is way lower than the cutoff point of -1.96. So our sample mean is in the critical region. This means that we would reject the null hypothesis, or our null hypothesis is very unlikely. So we would reject the null hypothesis. So -3 is much lower than -1.96. We could also say that our z obtained exceeds the z critical value. So another way we could put this, since our sample mean is in the critical region, is that our sample mean is significantly different from the population mean. This result is very unlikely if the null hypothesis is true, so we reject the null hypothesis. Prenatal exposure to alcohol does have a significant effect on birth weight. So step 5 is make a conclusion. So we would say that prenatal exposure to alcohol does affect birth weight, and the evidence suggests that prenatal exposure leads to decreased birth weight. So the difference in birth weight between pups exposed to alcohol and those not exposed to alcohol was significant. Okay, now that we've went through that example, let's kind of summarize, go back through the different elements of hypothesis testing we've been talking about. So step 1, we have a hypothesized population parameter. And number 2, we get a sample statistic as part of the process. We have an estimate of the error. This is variability in sample size lead to our estimate of error. We compute a test statistic based on the sample that we have and the estimate of error. We select an alpha level to compare our test statistic to the critical value. So all 5 of these things are necessary to begin hypothesis testing. Like I said before, there are some concerns about the hypothesis testing approach. One is that, so notice that we've kept making, when we make a decision, it's either reject the null hypothesis or fail to reject the null hypothesis. It's an absolute, an all or none decision. There is no middle ground here. The second concern is that the null hypothesis is artificial. We select the alpha level that leads to the acceptance or rejection of the null hypothesis. So it's kind of controlled from the outside. It's not reflected on a real difference. And the third concern about hypothesis testing, this is the most important for the remainder of the lecture, is the difference between a significant result and a substantial result. Just because our statistical test shows that there is a significant difference between groups does not mean that there is a substantial difference between groups, does not mean that the difference is large, even. One way we can address that last concern is through the measuring of effect size. So a hypothesis test evaluates the statistical significance of the results from a research study. The test determines whether or not it is likely that the obtained sample mean occurred without any contribution from a treatment effect. But the hypothesis test is influenced not only by the size of the treatment, but also by the size of the sample. So in this way, even a very small effect can be significant if it is observed in a very large sample. So how can we test the size of a treatment effect? Let's look at an example of this. So if we have a population with characteristics listed above, our null and alternative are listed here. Our treatment effect could be equal to or not equal to the treatment effect. Let's say after the treatment, we find that the sample mean is 81. So does this sample provide evidence of a statistically significant treatment effect? If we find a difference of 1 and we have a large enough sample, we could perform a hypothesis test and it would show that there is a significant difference between 80 and 81. So although that could be a significant difference, statistically significant, does that mean that that effect is meaningful? Not necessarily. So here are some example numbers using n is equal to 25. We could actually find in this case, we would fail to reject the null hypothesis. But what if we have n equals 400? Still, there's only a 1 point difference, but we reject the null hypothesis. So this is counterintuitive. This could be a problem. A 1 point difference doesn't seem like it should be statistically significant. So although a 1 point difference is statistically significant in that example, that doesn't mean that it necessarily has a large overall effect. So one way to test against these measurement errors or measurement discrepancies is to accompany a hypothesis test with a measurement of effect size. In the first few chapters where we'll be dealing with inferential statistics, the measurement of effect size we'll be using is Cohen's d. So Cohen's d measures the size of the mean difference compared to the standard deviation. And it does this through a simple measurement of the mean difference between the samples divided by the standard deviation. So when we go through that process and we have a mean difference divided by standard deviation, and we come up with a Cohen's d value, and there's kind of a general outline here on on this slide as to what constitutes a small, a medium, and a large effect for Cohen's d. So generally anything over 0.8 using this estimation is considered a large effect. Anything between 0.2 and 0.8 is a medium effect, and anything smaller than 0.2 is considered a small effect. So this is not the only measurement of effect size, but it's the only one that we're able to use right now. Later on we'll look at more. Okay, so we've went through the topics of hypothesis testing. This included talking about critical region, talking about the alpha level, and other concerns. Then we talked about effect size. The last topic we're going to talk about is the power of a hypothesis test. So the power of a hypothesis test is defined as the probability of correctly rejecting a false null hypothesis. So the power of a test depends on a variety of factors, mainly the size of the treatment effect and the size of the sample are what go into determining the power of a hypothesis test. So if we define the probability of a type 1 error as alpha level, as we talked about before, the probability of a type 2 error as beta, the power, which is the probability of rejecting a false null hypothesis, is 1 minus beta. So the power is 1 minus the type 2 error rate. This kind of defines power as the probability of obtaining sample data in the critical region when the null hypothesis is false. So you can see that because the data in the critical region is equivalent to rejecting the null hypothesis, these definitions are equivalent. Alright, let's look at this example here of the different things that can happen with an original population. It's normally distributed, has a mean of 80 and a standard deviation of 10. So if the null hypothesis is true, there's no treatment effect. We find a distribution of sample means here, and there's a certain region in which we would find no difference, but we would reject the null hypothesis over here. If there is an 8-point treatment effect, we find this separate distribution of sample means, but still, here is our critical region. Now, if we are setting up the null hypothesis test with reference to the population mean equal to 80, that means that whether or not the null hypothesis is true, or there's an actual 8-point treatment effect, we're still using the null hypothesis testing approach from the perspective of the distribution on the left. This means that if the null hypothesis is true, the part that's shaded in white, we would determine that there is no significant difference. The part that's shaded in blue, we would determine there is a significant difference. So if there is actually no difference, there is a large probability where we determine there's no difference. But if there is a treatment effect, then we're using this distribution over here, and there's only a very small probability right here that we would not find that difference. So this shows that the power of the test, if there is an actual difference, increases. Okay. As a final note in this lecture, I want to go back to the general form of all statistical tests that we're going to be coming up on in the class. These all take the form: the test statistic is equal to an obtained difference divided by the difference expected by chance. Each time that you encounter a new statistical test, so right now the only one we've talked about is the z-test for samples, but we're going to encounter t-tests pretty soon, and then we're going to encounter more. Always look at how those compare and contrast to this ratio. Obtain difference divided by a difference expected by chance. Or, saying the same thing, the difference between means divided by a measure of standard error. Okay, there was a lot of information in this PowerPoint lecture. I would advise you to read the book and watch this lecture. Please post on the forums before or after doing the homework assignments with any questions you have about this chapter, any clarifications. This is a lot of information, so I know there's going to be some. Thank you for watching.